please take your seats. Our presentations today are being recorded, and we ask that you please silence your electronic devices if you haven't already. Today we have 3 presenters on our agenda. Our first speaker today is Nilanjan Mukherjee, Senior Director of Engineering for Tessent Silicon Lifecycle Solutions. Nilanjan is currently involved in the research and development of key technologies in the area of test quality, test compression, logic BIST, and silicon lifecycle management. He is a co-inventor and an architect of Tessent Test Compress, the VersaPoint Test Points technology, and the Observation Scan technology. Welcome to the stage, Nilanjan.
Good morning, everyone. Welcome to ITC 2023. My name is Nilanjan, and again, welcome you to the Diamond event hosted by Siemens DISW. So the topic of my talk today will be advances in shift-left DFT, how our customers are actually using the DFT implementation or implementing DFT in RTL to enhance or to able to verify in RTL, thereby reducing the time to market. The agenda of my talk will be as follows. I'll start by talking about some of the challenges of growing time to market. Then I will address some of the solutions that can actually help alleviate those challenges. I'll briefly mention about the shift-left evolution, then talk about the tools for RTL DFT implementation, and finally summarize. So if you look at the graph, the left side, the left graph, it actually, to meet the society's demand for semiconductor ICs, the number of ASIC design starts has been growing steadily over the last 7 years, and it is expected to grow at a CAGR of 5% in the near future. On the right side, the graph shows the challenges, the engineering effort that is needed to implement an IC as we move towards lower technology nodes. As we move from 7 nanometer to 5 to 3 to 2 nanometer designs, the amount of engineering effort that is needed increases by 55% for every node. The way we are addressing it today, we are throwing in more engineers, more bodies to do that work. But that may not be sustainable. That is not sustainable. And what is exacerbating is that problem is the availability of skilled resources that can work in the engineering, in the semiconductor design industry. So this is a study that was, that BCG, the Boston Consulting Group, came up with, which showed that by the year 2030, the number of skilled workers that are needed in the semiconductor industry will grow by 50%. Whereas the number of skilled engineers that we will be producing will grow only at 1% rate. So by 2030, there will be a shortage of engineers by at least 35%. So just throwing in more engineers to the as the complexity of the design increases is not a scalable approach. So what did we do? What are some of the challenges of growing time to market? If you look at it, the factors that affect the time to market are the design, technology, and system scaling. So as we move to lower technology nodes, like for example, FinFET to gate-all-around to nanosheets, the complexity of the design is increasing. Similarly, the design complexity, if you look at just the design complexity, how do we now partition the designs so that it can actually fit into multiple dies to get into, basically go into 2.5D or 3D IC packages? That is also putting pressure on the time to market. And then, as I already mentioned, the lack of skilled resources is creating or exacerbating this entire pressure on the time to market. So how do we address some of these challenges? So there are some proven strategies or proven technologies that are already being used across the industry. So one such is the hierarchical DFT techniques, right? You can implement DFT across, like at the board or the tile or the core level, so that you can actually parallelize the activity across design teams or across geographic locations and reduce the total implementation time. That not only reduces your implementation time, it also reduces the amount of the machinery, the machinery that is needed to complete the task. Similarly, shift left as another strategy where we see companies are increasingly doing some of the tasks or some of the DFT implementation in RTL rather than at the gate level. So that improves the design cycle time because it reduces the number of iterations that you need to do when you find problems later in the design cycle. And then finally, with the lack of skilled engineering resources, we need automation. There's a lot of talk about expert systems, AI, how that can help improve the productivity of the DFT and the design implementation teams. So if you look at the requirements for shift left DFT methodology, what are some of the key requirements? So those can be divided into three categories. First is analysis, insertion, and verification. So on analysis side, if you are doing DFT implementation, you would like to understand you'd like to run some of the design rule checks at RTL. You'd like to understand the complexity of the RTL in terms of and how it contributes to testability. You would also want to do things like test point analysis early in the design cycle, wrapper analysis to isolate your cores, or even X-bounding analysis to improve compression or actually block all the excess so that you can implement logic-based. As part of insertion, you want to insert all the test instruments early in the design cycle in your design so that you can verify as much as possible. You would also like to have tools that can actually edit your designs and deal with some of the complex constructs, the system Verilog or the Verilog system Verilog constructs in your design. And also one of the most important things is you want the tools to preserve the look and feel of your RTL or look and feel of your design. No one likes, if you have coded your design in a certain manner, you wouldn't like to come and see that the tool completely messed up the same. So you would like to preserve the look and feel. And finally, on the verification side, you want to simulate and verify as much of DFT as possible early in the design cycle or in RTL. So things like equal verification. You have your IJTech network. You want to verify that network. You have SSN bus already in there. You want to run some tests to verify the SSN bus. You have logic-based implemented here. You want to run some self-tests to make sure that the controller is working correctly. Then you also want some of the debug capabilities. So if something is not working correctly, how can I figure out what is wrong and how do I take corrective measures? So some way to also get an impression of what will be your ATPG test coverage, what will be your pattern count. Are there some outlier blocks that need special attention? If you can get that information early in the design flow, you can then take corrective actions, corrective measures to improve the overall testability of your design. So let's look at the DFT shift left evolution. So if you look at 2 decades back, 20 years back, right? Most of the DFT was implemented or inserted and implemented in the gate level. So you go through synthesis, you insert all your DFT, then you actually do some incremental optimization to make sure that your timing closure is still there. So you want to make sure that design closes timing. And then finally go and do generate ATPG patterns. But over the last decade, things have changed. Most of the DFT insertions, like memory-based, the repair IP, the IJTAG, OCC, logic-based, test compression, SSN, all these things are now inserted at RTL. So you have the opportunity to implement that, verify those, and see how those are working early in the design cycle. The only thing the few things that were still done at the gate level are things like test point insertion, wrapper cell insertion, or X bounding logic or scan stitching, right? What we are doing now is providing tools so that you can actually also do test point analysis and insertion, wrapper analysis and insertion, and X-bounding analysis and insertion at RTL. So you don't need to wait until the gate level. So this allows you to write out the RTL after all those DFT are implemented. You can do your equivalency checking to make sure that the design is still working. And you can also, in some cases, verify how, like, whether they are working correctly or not. So that reduces your iteration time, because if you insert things at gate level and you see things are not working, you have to go back to RTL, make some changes. But this allows you to look at your design, to implement all the DFT and verify that DFT at RTL. And there are other options where you can do these things as part of synthesis, but this is even better as it allows you to write the RTL. And it is not, the output that you get is an RTL, which you can still simulate and verify before you go to the synthesis process. So the last three, the test points, wrapper analysis, and X-bounding, this is what is part of a new tool called RTL Pro that we announced yesterday at ITC. So what are some of the key features of RTL Pro? It does a quick RTL complexity analysis and reporting, so you know what are some of the complex RTL modules that you have. It also does an analysis of the RTL to let you know whether that design is suitable for test point insertion in RTL or not. Because there are certain designs, if it is completely very control heavy, everything is in the control logic, RTL test point insertion may not be, you'll not be benefited from that. You may have to do some parts of it at the gate level. So it actually tells you, advises you whether you can do the test point insertion or some of the other analysis at RTL or not. And then it does the analysis insertion of the test points, wrapper cells, and X-bounding logic. And this is actually consistent with some of the RTL DFT capabilities that exist across all the Tessent tools. So today, our tools already allow you to do design rule checks. It allows you to do design editing. And it also generates things like IJTAG gray box that simplifies the view of your design, that actually allows you to speed up the simulation. It also, as I mentioned, preserving the look and feel of the RTL is very important. So it already does that. And we try to minimize the changes through the blocks where you are not touching. And it also, the tools are capable of handling complex Verilog and system Verilog constructs that are in your design. Things like system Verilog interfaces or generate loops. And under the hood, the tools have the quick synthesis engine that allows you to quickly synthesize your RTL, do scan stitching, and run ATPG so that you get an idea of what your test coverage and pattern counts are. And this is much more accurate than some of the estimates that you can do at the RTL today because it doesn't match with reality. So in summary, so the productivity challenges will continue because of the design, technology, and system scaling. The innovations in RTL, DFT implementation, and verification will continue to improve, which actually will allow you to reduce the time to market. And then Tessent RTL Pro extends the shift-left DFT strategy by moving the implementation and verification to RTL. Thank you.
Our next presenter today is Darshan Kobla, Senior Director at Microsoft, leading test strategy across all product segments. His team focuses on pathfinding, evaluating and adopting industry trends in test with a laser focus on test cost, quality, and time to market. Prior to joining Microsoft, Darshan spent almost 2 decades at Intel Corporation in various roles. He graduated from Arizona State University and is a proud Sun Devil. Please welcome Darshan and his presentation titled Smart DFT for Complex Semiconductor Designs. Welcome to the stage, Darshan.
Good morning, and thank you for having me. Let's start with a quick poll. How many can resonate Microsoft to software? Most of the audience here? okay? How many can resonate Microsoft to Xbox? Quite a few, okay? How many resonate Microsoft to hardware? A few hands are going up. How about cloud? Okay, few more hands are going up. Well, over the last decade, Microsoft has transformed from what's being known as a Windows-based company to one of the leading cloud providers with an end-to-end hardware and software solution. You can see the footprint of Microsoft Cloud across the globe here. And we have huge data centers, and there's a little picture of one of the data center in Europe that is under construction. So with that in mind, I'm hoping when we walk across the hallway, you can come back and say, hello, Microsoft, hello, Silicon. Okay. So the next couple of slides is going to talk about the industry trend. And what this slide shows is the disruptive technologies in the past 2 decades mapped against the time to adopt these technology. Take from the beginning, we've got cell phones. Almost everybody has a cell phone in their pocket. And it's been around for the last 2 decades. It took over 16 years to reach 100 million users. I'm going to fast forward to the last one there in that chart. You've got many disruptive technologies: Facebook, Twitter, Instagram, TikTok. The last one is ChatGPT. It started with the OpenAI alliance with Microsoft in 2019, and ChatGPT was introduced last year, and it reached 200 million users in 2 months. So what does this mean to our industry? AI requires a lot of compute power. That means we have to build large chips, integrated chips, and we have to come up with smart DFT solutions like Nilanjan was alluding to. We are going to have large complex chips. There's absolutely no way we can throw more people to solve that problem. Okay. So I'm going to move on. I'm just going to continue with the industry trend, and I'm going to talk about, what are the challenges we are seeing in DFT? Obviously, the whole theme of the conference today is heterogeneous integration, 3D. And that's one of the biggest challenges we see as a DFT engineer. You have limited pins. You're not able to access all layers of the chip. And you still have to get your DFT done at the required quality. And then the sizes of these chips are growing inside a package. Now, what used to be a quality requirement for a chip now becomes the quality requirement for this entire 3D IC and the package. And as you can see from the William Brown model, as the chip size goes up, you're going to have defects that are going to go up, and we need to come up with much smarter DFT methods and scalable to cover these challenges. There's always a push to get the cost down, right? Any DFT engineer, any test engineer, there's always this thing of get the quality, but keep the cost low. And that's going to continue with heterogeneous integration as well, right? It's not going to be new. And then the 2 slides ago, you saw our big data center. One of the biggest problems anybody in this market faces is silent data corruption, and that's not going away. It's a big challenge, and it's going to be discussed continuously in this conference and in the years to come, right? Until we come up with some very innovative solutions to tackle this problem. Okay. And then some of the practical constraints that we have is, many of you come from various DFT test teams. The common trend, the common thing that you hear is shortage of talent in this industry. There's always, you take a DFT team, you talk to anybody, they will tell you, I need about 2 more resources, I need 3 more resources to be in my optimal sweet spot. And this is a constant problem, right? And Siemens has somewhat added to this problem by, coming up with constant innovation in their technology so that the engineers have to keep up with it always, right? And next one is compressed design cycle. I mean, this time to market component that you you have to, get all the stuff done, and the cycle seems to be shrinking every single time you go start a new design. Right? And then the last one, and it's very important in your silicon lifecycle management, is predictability in silicon bring-up. You can do all this good stuff. You can put your DFT, you can do verification, you can shift left, but when the silicon arrives, and if there is a delay in bring up, as a test engineer, there's a gun on everybody's head to get this out on time, and that predictability is needed to keep this whole silicon lifecycle under control. And more importantly, right, this is very critical to launch products on time, to reap the financial benefits. There's a lot of implications that lie on this, right? Okay, so I'm going to go one more slide. I'm going to talk about some of the industry trends here. And I'm going to use this little cartoon to explain this problem. We had our keynote speaker earlier today talk about heterogeneous integration, talked about how you build chips. It's almost like Legos that are snapped together these days. You get IPs from various process technologies. You have replicated IPs. They're all snapped together. You need to find a way to do this design. And the problem is no different from how you do this from an RTL perspective, from verification perspective, from DFT perspective. They're all the same, right? You have to break it down into smaller jobs, smaller partitions. You have to do, and the same thing is done with the RTL engineer. An engineer designs a small chunk and does not design the entire chip. Same with verification, same with physical design, and DFT also uses the same approach. Except that now, DFT being an interdisciplinary skill that you have to go not just from your tiny little RTL, not from your tiny little physical design block to your chip. Now you have to extend it all the way to your package, and then you have one layer up there, which is 3D, that is also sitting on your chip, right? Again, this is a mock-up. This is not a silicon that Microsoft designed, just to be all legal. But I'm trying to explain the concept here that, we've got this. Then the next problem that you face is you're reticle limited. So what this means is, in order to achieve your performance targets, you might have to replicate this chiplet multiple times. Okay? And then you also have chiplets that are stacked 3-dimensional, and you also have chiplets that sit on various different process technologies. Right? So how are we going to tackle this? The same thing. It's all going to be based on hierarchical design. You tackle this at the lowest level, at the smallest hierarchy, and roll it all the way up. And if something is not available early on, just black box it and move on. Right? That flexibility is absolutely required, and that's the only way we're going to win this game. Next is flexibility, right? There is there's very little room, as you see in our design cycle, that you want to really, really, really do this ahead of time, very early in the RTL, do flexible, like multiple insertions of your DFT, try this out, and then, it's almost like, you're ready to go to Super Bowl, but you've done all these practices, multiple runs, and then your final run is like, you hit, multiple touchdowns after touchdown. You are going to do a really good job if you can have complete flexibility and do all your designs ahead of time, like insert DFT ahead of time. Then comes pattern generation. This requires absolute flexibility. Nobody knows when you start the project. Of course, you have power targets, right? But you have many things that come into picture that you have to be flexible enough that you start off telling that I'm going to design it this particular way, and then your entire pattern architecture or how you're going to do your patterns will actually, completely change once silicon arrives. And you have to be flexible enough to react and regenerate your patterns very quickly. And at the end of all this is automation. That's the key. Otherwise, we could have this room full of resources and we're never going to get even half of that chiplet done. Okay, so here's a little story, right? When Microsoft Silicon started, we had a few options, right? It was large design. And then we said, okay, so what do, right? We start with a traditional EDT-based design. We could bring up the channels, and then, when we started drawing up on the board, we ran out of space, and that just tells you how complex it was. And it was not manageable, right? At that time, we looked outside what was available in the industry. There was hardly any solutions that was available. And one option is to build something, and then the other option is to look at an emerging solution from Siemens, which is SSN. And we took that risk. We started our designs with SSN when it was, in its very early stage. And there was multiple challenges here. We have a design team which is fairly experienced but brand new, and we have things that are being put together for the first time. And we had to go through multiple iterations initially to get things to work, right? So we stuck to SSN. We had all the flexibility. The flexibility is to the extent that, I didn't have to do a lot of pre-planning, that, I need to have these many EDT channels. I didn't have to do a lot of pre-planning. SSN gave me all that flexibility to just go and take a scalable with bus. As long as I used a method that I was floor plan aware and I ended up routing it, I could, bring this up and make very, very late changes, right? I mean, there will be always changes of, this portion of the floor plan is going to move from north to south, east to west, and vice versa, and DFT has to react to it in overnight or in a few days kind of situation. And this is very common. This trend is very, very, very common, right? What came with that is the adaptability that you had a scalable network, very flexible, just like Legos that you end up moving around, and you have a configuration network to go with it, which is IJTech, right? The next piece is the cost, right? We've got patents, and you want these patents to be super tight compressed so that we could put it into a tester and achieve the quality, right? That whole benefit of reducing any kind of white space, time domain multiplexing, gave us that cost benefit. Okay. Now the next one is going to talk about something that's near and dear to me, our team, our management. When we started this whole Silicon initiative, we were given by management two challenges, right? First thing they said, well, as a test community inside Microsoft, you need to meet quality schedule. That's your first challenge. There was no trade-off one way or the other. You need to meet both. And you need to be absolutely predictable on the dot how long it will take for you to bring up silicon. And these are some of the things that we did to achieve that. Okay, first thing, very small team, relatively new. And what we had to do was just stick to industry standards, right? Straight out of the box solution, nothing fancy, plug and play, completely flexible. And when we put things together, we went to our EDA partners and we did an architectural review. I mean, there was very valuable feedback that came out of that review because, they said, hey, these are the things in your design. The tool is going to not do its best, but, you could do it this other way or vice versa, right? There was always that cycle of feedback that was very, very critical to, getting us to this successful state, right? And then diagnostics and debug. I can't say enough how critical this is, right? I mean, it cannot be an afterthought. In fact, we start thinking about diagnostics and debug right from day one. We start building models and trying out, just like any other milestone in DFT. This is a very important milestone that we start very, very, very early on. It's not an afterthought, shouldn't be an afterthought, right? Next one is how do you build around these tools, right? All you have to do is just keep the junior-most engineer in room in mind and think how that engineer is going to use it. You just have to keep it really, 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 really simple. Use it out of the box. Simple scripting automation around it. Everybody can see what switches are going on. And it's very important to have consistency. That's why we are automating things, right? I mean, I'm going to run this tool today. Nilanjan is going to run it tomorrow. Janusz is going to run it the day after tomorrow. It should just give the same result. It has to be predictable, right? And then the other thing is, right, you have to have that flexibility that, you can scale and you can also make quick changes. Okay. So the next big aspect, right? I mean, DFT and physical designers are like, buddies, right? They're like locker room buddies. And you have to be, really good pal with them, for the chip to be successful. And some of the things that we have seen is, in order for your DFT to be successful, you really have to do your design floor plan aware and think about all the floor plan stuff that you would do. You take all the feedback on your floor plan, just go ahead, right? Do it right at the RTL. Do not wait till you go up to the netlist, just push it all the way up. And this little diagram I put that's got number 1, 2, 3, and 4, it's like one of those cartoons where you say, hey, look at these things and find the differences in each and every block, right? And if you look at block number 3, it's missing a repeater. That is a horrendous climb in the design world because, you will have a lot of problems if you're missing that on timing closure. Be generous on repeaters when you're doing big chips. It'll save the bacon at the end of the day. And then clocking. Clocking is very, 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 very critical, right? I mean, if you look at this picture, there's no physical connection from 1 to 3. Why does the clock need to be synchronous and time close between 1 and 3? I mean, you could pretty much go ahead and do your clock tree, but ignore the endpoint and make it just source synchronous. The next one is completely, localized kind of design when you're doing timing closure, right? All your signals have to be locally generated. And that's the only way, you can keep it manageable. The more global stuff you have all kinds of penalties that go on. You have crossing, you have OVCM, and if you have to meet hold, you have to have DSKU latches or negedge flops, and all kinds of complexities come in. The more you can keep it localized, the only thing literally you want to go across from your physical partitions is your SSN bus, and as long as you cleverly plan it out, you're going to be in good state. The next problem is really important: the power delivery and timing closure. A lot of things today, as you see, your package is now your SoC. A lot of power delivery aspects now come together in package. So what do you do in wafer sort? In fact, you're dealing with a situation where your wafer conditions of power delivery is different from what you see in package. And you have to take that into account very well ahead of time. And timing closure, this is not DFT is not a poster child, right? It's not something, that you have to treat it in par with everything in your design to make this work. Okay. So I'm going to move on really quick here. Next, I'm going to talk about verification, right? So there are all these kinds of verification that you do. RTL, gate sense, you do at the IP level, you do at the SoC level. You've got great gray box, black box technology that lets you do full chip simulation. I mean, for these sizes, you would never even think it's possible, but it is doable today with great gray box, black box kind of technology. But one thing really important to look into here is the effort to do verification. It keeps going higher as you go up this chart. And then on the other hand, the ROI to find bugs is inversely proportional. So what this tells you is, do most of your work on, in fact, everything other than your scan stitching, wrapper cells, do everything in RTO, and but then don't skip the other steps. That's the key message. Don't skip the other steps. That's really required to get your predictable silicon. It's your nth order, some kind of global interaction that you would miss out, that you need your SoC sims. Okay, patents. I mean, this is near and dear to me. You have to just stick to industry standards because they've solved it for you. As long as you can take all the tester timing information, put it back, regenerate the patterns exactly the way you want your tester waveforms to look at, your pin levels and timings are there, then all you have to do is take small number of patterns, run it against RTL to make sure that you've not messed up anything and you're good to go. Okay, so just a quick recap there. Do your simulations, everything possible at the RTL, do all your insertion at the RTL, do all your depth simulations at the chip level or your gate level, or at your IP level. And then once you move to chip level, just keep it to make sure your interconnectivity and it's no different than what we said on timing, right? It's in fact the same concepts follow, but don't skip SoC level simulation. Okay, I'm going to conclude here. If there's something I can, you want to take away from the last 20 minutes I spoke, just keep DFT simple. Keep it straight out of the box, stick to industry standard. That's the only way you're going to get to a predictable silicon. I'm going to leave some do's and don'ts here and conclude my presentation. And I want to thank Siemens for this opportunity, ITC for having me here. And last but not the least, if there's time at the end, I will not answer any questions, but you're more than welcome to catch me after the presentation or during lunch, and I'll be happy to answer anything. Thank you.
Our final presenter today is the Vice President and General Manager of Tessent Silicon Lifecycle Solutions, Ankur Gupta. Ankur has more than 20 years of experience in digital design, implementation, and sign-off. He was previously Senior Director of Product Management at ANSYS and worked at Cadence Design System, where he oversaw the first 5 developments of RTL to GDS2 to the market. Welcome to the stage, Ankur.
Thank you. Thank you for the introduction, Jonathan. Good morning, it's still morning, and hope you have enjoyed the presentations from Nilanjan and Darshan. So look forward to talking to you all offline. I'm going to start my talk on how to engineer a smarter future faster with this picture. This is a midjourney.ai generated picture, which I just did this weekend. And the prompt was, show me a picture of a data center with nature inside and outside. So this is the sort of, took about 1 minute, and actually says, okay, give me some time, I'm generating the picture, and before I could blink, the picture was there, but it's doing this compute and generating something that is unthinkable even 4 or 5 years ago. So the smarter future is here, and we in the EDA community are helping realize this future even faster. Now, Darshan presented one view of how these chips that we are talking about today, AI, ML, hardware is accelerating. This is a chart from Siemens. We've done this study, which shows the value of AI, ML as a vertical market on the overall $1 trillion market that we are all together building by 2030. If you pay attention to the darker blue shade, that's the AI, ML hardware that we are seeing, that we're going to see in the next 7 years or so. The rest of it is designs from other vertical markets. Overall, the CAGR is 32% over the last 10 years. Now, if you subtract out the AI ML hardware, which is enabling the smarter future, then the CAGR is about 3%. So truly, as an industry, we are being driven by this bespoke silicon. You heard the other speakers this morning as well talking about bespoke silicon. So that's bespoke silicon content. The hardware, which is supporting the software, like the picture that I drew on Midjourney, is where our industry comes in. So exciting times. Another view of these exciting times was presented by Ganesh Venkat from Tesla just recently at the Hot Chips conference, and I thank Tesla and Ganesh for letting us use this slide. Here he talks about 122 years of Moore's Law and how we have all been driven as a community by this vision from Gordon Moore. And pay attention to the very last part. Ganesh says that we are now switching from integrated circuits to integrated systems, which is very true. Today's theme at ITC is 3D IC. Tomorrow's theme is AI, and day after's theme is Silicon Lifecycle Management. You bring all of those 3 things together with these integrated systems, these systems are being driven by vertical markets like autonomous and data centers, and they have to be built on advanced packages. So not just integrated circuits, but integrated systems like Darshan just mentioned, you need advanced packaging to build these systems out. So that's the era that we are now getting into. The question though is, can we engineer this next phase of integrated systems by doing business as usual? Now, don't get me wrong, business as usual is already great. You just heard from our speaker, Nilanjan talked about RTL, Tessent RTL Pro, which we are very proud to introduce to the market today. That's shift left. Darshan talked about SSN. Last year at the same event, you heard Dan Trock from Amazon talk about SSN. So that's business as usual. That's today. That's already very powerful. But what is in store for us is even more challenging. And the way to think about it for us as a test community is, can you sufficiently test these complex SoCs and systems that are being built by customers today? On the left-hand side is the SDC challenge, silent data corruption challenge. I'm just putting pictures of papers that have been written about this challenge recently. On the right-hand side is the autonomous vehicle enablement challenge. Now, on the left-hand side, since the SDC papers came out about 2.5 years ago, as a community, we've been studying what is causing these silent data corruption issues. And the general consensus seems to be that there are escapes, there are latent defects, and there are escapes. Now, that is a function, first and foremost, of software bugs. But it also is a function of hardware variation due to voltage variation, temperature variation, frequency variation. And that's where we come in to design better methods to identify these latent defects. On the second front, on the autonomous front, this market is being pushed very quickly towards FinFET nodes, because they have to put everything, including the microcontrollers, the engine control units, side by side with the infotainment system, and all of that fits on a single node on FinFET. But guess what? The high quality requirements that the autonomous and the automotive market has, which is DPPB, parts per billion, that is not a solved problem necessarily in FinFET, because the other vertical markets that have already been using FinFET have been doing low DPPM, but not necessarily low DPPB. So net-net, when we at Tessent look at all these market trends, we see this as the evolution of test beyond what we are delivering today is absolutely necessary. And we have to look at software and hardware co-design to keep this next phase of evolution in mind. Now, why co-design hardware, software? If you look at the use cases, these are the hardware that we are designing, the software workloads that it's running is being generated from variety of designs, not just cloud data center or enterprise applications, but even small, medium businesses or small offices, home offices, myriad type of applications are running on this hardware. And that hardware or the software is being executed in diverse environments. It's being executed on the cloud. It's being executed on enterprise servers, on edge servers. Plus, the hardware itself is seeing a lot of change. There are CPU subsystems, there are accelerators, there are different types of NOCs that are constantly evolving. Even the instruction set architecture for x86 or ARM or RISC-V has to be taken into account. So designers have a significant challenging time ahead of them. Net-net, we look at all of this put together as safety-critical applications, be it for automotive or large data centers. And our thesis is that you've got to look at high quality of test, not just for pre-silicon phase of your design, but now also for the post-silicon phase of your design. So that's a key change that the market has to look at. Beyond testing, there's also in-life monitoring and in-life analytics, which is the silicon lifecycle management part of our overall goal that is evolving very rapidly. And this is all becoming reality. Step back for a second and let's look at what is a typical flow today. So this is a traditional emulation prototype simulation-based flow. You see there is some feedback loop, but that's all pre-silicon before tape out. Once the chip is taped out, it's like you lose visibility very rapidly. You can't really tell what's happening to the health of this device as it goes through the second half of its journey, which is a significant portion of the journey, the post-silicon journey. Now, ideally, if you could add post-silicon visibility into your development flow, then we could have a lot of feedback loop even post-silicon. And that allows us to detect and fix defects, co-optimize hardware and software. It allows us to look at the secure capabilities while the chip is in system. You heard some of the speakers this morning describe how we need to worry about security. And then system optimization, field debug, RMA, visibility of RMA, those are all important things that become feasible and possible. Now, visibility of RMA, just to spend 30 seconds on it, is very important. Think about hyperscalers, such as Microsoft or AWS or Google. When they have a failure, they essentially go to their ASIC vendors and say, okay, there's something wrong over here, you go debug. But the ASIC vendor receiving that device doesn't really have a lot of data that comes with it. Why did it fail? Was it a software issue or was it a hardware issue? This goes back to my silent data corruption slide, where I said that escapes could be a function of software bugs. It could also be a function of hardware variation under certain workload conditions, environmental conditions. This is all really hard to debug if you don't have visibility or the ability to capture the environment when that device was running in the system in its in-life use case. So this is becoming critical to build for us as a community. So what are we doing at Tessent? We're looking at this entire gamut of design, production, and in-life challenges and looking at it from the lens of structural test and silicon lifecycle management. Now, this is a slide that's hopefully familiar to many of you. We've been describing this in our meetings with you, as well as in technology forums. What I want to do is spend a few minutes to draw attention to a few things over here. First, there is a need for higher quality of tests. Second, things like stress tests to understand and expose latent defects. There's a need to do more over there. Third, there's a need to do system level tests, because as the higher quality of tests and stress tests increases and improves, there are more patterns being generated. So you can't run all these patterns on the ATE. You want to be selective about what you run there, and you want to carry the rest of the workload over to the system level tester. Fourth, diagnosis, e-learning. This is extremely important. AI, ML enabled diagnosis, because this is a big data problem. Fifth, the system level test should really carry over into the in-system. Why stop at the system level? You should carry this over into the in-life use case. And finally, whether it's in the lab or in system, you need to have remote orchestration for the hardware-software interaction and to be able to inspect the code as it's being executed so that you can identify, basically do functional monitoring. Now, we as a team, the Tessent team has been investing heavily in each one of these areas. In conferences such as ITC India this year, Nilanjan presented a talk that showed that for high quality of test, we have already been doing a lot of defect-oriented testing, but we are doing more. We are introducing timing awareness in cell-aware test so that you can identify near critical paths which can become critical because of accumulation of small delays. You can do more. You can study these paths across critical corners. It's not just a single corner world that we live in, it's multi-corners. On the stress testing side of things, we are working with key semiconductor partners to develop higher quality of stress test. On the system level testing side of things, we have under development capability to enable these high quality scan tests on a SLT. We are working with our partners on the testing side as well. And then yield learning and diagnosis. As I mentioned, this is a big data problem. We have already introduced ML-based techniques to identify very narrowly top 1 or 2 suspects. What you see in the circle is when you apply ML techniques, we are able to get down to very few suspects, which is what you want in diagnosis. Now, the population of defects where we are able to do this is still maybe a quarter of the population. The industry requires us to improve this and make it so that 50% of the overall defects can be diagnosed this way in software. And then for the monitoring and debugging with the software running on the hardware, we have application thread timing, CPU performance loss monitoring capabilities using our Tessent embedded analytics. These things are in various forms and shapes are already in production or in our roadmap. For this final piece, if you haven't already checked out a paper by Richard Bone from Seagate, he presented at the user-to-user conference, the Siemens user-to-user conference earlier this year, very powerful paper on debug and optimization strategy and how it enables Seagate to build the next generation disk kind of management with, I think he said 30% faster, better capabilities. So a strong suite of products that already exists, but as I mentioned, with things like RAS events, firmware changes over the air, and so on, the complexity is still increasing, and we need to do even more in field. So our vision, in a nutshell, is to build a digital twin of these complex devices and systems, these integrated systems, as they exist in their in-field life cycle. So with all of this, what do we hope to enable? For the chip developer, if you integrate the DFT capabilities that I just described along with monitors, you'll have Tessent-enabled devices. You should be able to get higher quality of test, higher reliability. With that, you should be able to design your smarter devices faster. For the embedded system manufacturer, this implies that you have these Tessent-enabled devices in a fleet, and you should be able to do the in-system testing with remote orchestration, monitor safety secure transactions, and the remote debug should enable you to quickly make changes as required. And the system operator also benefits tremendously because there is a CapEx, OpEx related to operating these data centers, these autonomous devices, 5G baseband stations, which are kind of working under very harsh conditions. The the service level agreements, the SLAs for these harsh environments are very stringent. So we should be able to enable you through these kind of product lines that I just described. And finally, this is all designed to help us get there in a sustainable manner, because our community does need to think about sustainable development from here on. As an example, the data centers that we are talking about, today's data centers, they consume only 1% of the total electricity that the human population consumes. That's 2023. By 2030, when our industry becomes $1 trillion industry, the growth driven by data is going to be 100x. compared to now. So if we just keep building data centers as they are, that 1% of electricity consumption today doesn't scale. So Microsoft, and I'm taking Microsoft snippets over here because Darshan was in the audience today and was a guest speaker. Microsoft has high goals for things like server lifetime extension and reducing the carbon impact. Siemens understands this very well as well. Siemens as a company, not just DISW where we sit, but the overall Siemens has committed several efforts to achieve carbon neutrality by 2030. So with that, I will end my talk. Let's get to a smarter future faster, also keeping carbon neutrality in mind. And this is the community that can help get us there. Thank you.
Thank you all for joining our Diamond Sponsor presentation session. For additional information about these topics and more, please visit Siemens at booth 205 and talk to a representative. Booth theater presentations are scheduled during breaks and lunches, where you will see presentation on our various topics presented by our customers, partners, and Siemens representatives. Please stop by to enter our daily drawing. Thank you and enjoy the rest of the conference.